Hi, my name is Garrett Clark, and I chose to do my research project on a game theoretic approach to the optimization of swim teams. So, most kids, when they're younger, take swim lessons of some kind, but not many kids have competitive swimming experience. So, what is competitive swimming? Well, it involves the four types of strokes. You have freestyle, backstroke, breaststroke, and butterfly. And each of these have their own kind of styles and technique to the way you swim, and basically get you down in the pool faster or slower depending on which stroke you do. Now, once you become a pro at these four strokes, you have to have a venue to compete in them, right? So these are called swim meets, and each swimmer basically joins what is known as a swim team. And these teams compete against each other to see which team overall has the better swimmers. So each meet is composed of approximately 13, 14 events, depending on the event lineup. Um, these events include individual and relay events, but for the purposes of this project, I focused only on the individual events. There are 12 individual events every meet, usually. It's the 50 yard, 100 yard, 200 yard, 500 yard, and 1,000 yard freestyle, the 100 and 200 yard backstroke, the 100 and 200 yard breaststroke, the 100 and 200 yard butterfly, and the 200 yard individual medley, also known as the IM, which is basically 450s of each stroke. Now, in each meet, when a coach is deciding which swimmers to put where, there are rules that that coach has to follow. Each swimmer can only swim up to 3 individual events, and each event can only have up to 3 swimmers competing in that event. So, how do you win a swim meet? Well, points are awarded based on where a swimmer places relative to other swimmers in each event. So if a swimmer gets first place, he's awarded 9 points. If a swimmer is awarded second place, then he gets 4 points, then 3 points, 2 points, 1 point, and then the sixth place person gets no points. It's a coach's job to know which events to put each swimmer in order to optimize the amount of points that each swimmer scores. There are two key themes that a coach needs to realize when he's choosing which events to put a swimmer in. First of all, the swimmer's time doesn't matter as long as he wins the race. A swimmer could be Michael Phelps and beat everyone by at least the whole body length. But if another person beats them by .01, it doesn't really matter. The time itself doesn't matter as long as the person gets first place. Also, a swimmer should be placed in events that they're good at. That just makes sense. If they were put in an event that they had never swam before, then they're probably not going to win the race. So, putting people in events that where they can beat other swimmers in makes a huge difference. In order to maximize the amount of points scored in a meet, it becomes important to model a swimmer quantitatively. First of all, each swimmer has a list of main events that they typically swim well in, and we should only really put a swimmer in an event that is one of their main events. Then, for each main event, a swimmer has a best time, signifying the fastest time measured in seconds that they have ever swam in that event. Typically, if a swimmer has a faster best time than another swimmer, he will probably win that event. For example, Joseph Waters here has 4 main events: the 100 butterfly, the 200 butterfly, the 200 IM, and the 50 free. And these are a list of his fastest times in those events. Once we have modeled a collection of swimmers, we can begin to quantify a team. First of all, each team has what is known as a roster of swimmers. This is basically just a list of all the swimmers that are on the team. When a team enters a meet, it has a lineup where each swimmer is assigned to a set of events that is a subset of his main events. This means that for each event, a team will assign a swimmer to that particular event, depending on if that event is in their main events. Also, the team must adhere to the rule that it cannot assign more than 3 swimmers to an event. Here we have an example roster for the Tri-County Flying Sharks. This team has 5 swimmers: Bradley Cooper, Thomas Jefferson, Johnny Appleseed, Jack Black, and Donald Trump. And these are a list of their events and their best times. And here's an example lineup for the team for a potential meet that could happen. As you can see, there isn't more than 3 people in each event. Because the team was slim, there's usually only 1 or 2. And then each swimmer is only in 3 events maximum. Well, now that we have a model for swimmers and swim teams, we can begin to model a swim meet as a game. Now, for this project, I decided to take a novel approach when trying to optimize the swim teams. I decided to imagine that 2 coaches were playing chess, where each swimmer was a player, basically, and a piece on a board. Uh, the players are the coaches, and each coach takes turn placing a swimmer in an event. And then the goal is to play the swimmer that is most optimal each time. The first thing to note about modeling the game in this way is that this is a game of complete information. Both coaches are aware of the main events and best times of each swimmer on each team before the start of the game. This is not a game of perfect information, though, because neither coach knows where the other coach has placed his swimmers at any point in time. This is similar to playing chess blindfolded. Um, Assuming that each coach has played optimally, though, we can play the game for each coach and place swimmers for both teams if each move is optimal. Another thing to realize is that this is a zero-sum game. In order to win, a team must have more points than the opponent. We shouldn't really look at the scores of each team, but the differences between the scores, because that's what really matters. If a team has a greater difference than the other team, then that team is going to win. If we let S sub A be the score of Team A and S sub B be the score of Team B, the score of the meet should be S sub A minus S sub B for Team A, and then S sub B minus S sub A for Team B. For example, if Team A has 100 points and Team B has 110 points, then the score of the meet should be negative 10, 10. At this point, it becomes important to define what a move is in the game itself. We can let a move be defined as entering a swimmer into an event. A swimmer can only enter an event that is one of his main events. If a swimmer is currently entered in less than 3 events, he can be entered in a new event that is one of his main events. If a swimmer is entered in 3 events already but has more than 3 main events, he can be removed from one of those events in place of another one of his main events. Now that we know what a move is, we can start figuring out what an optimal move would be. First of all, each move should try to maximize the increase in points relative to the other team. We can let D sub A be equal to the difference of S sub A and S sub B, and then similarly for D sub B be the difference between S sub B and S sub A. Now, when it comes time for a coach to make a move, these differences will be affected because the scores of the meet will be affected. So we can let D sub A of M and D sub B of M be the new differences given a move M for each team. Define an optimal move for Team A to be the move that maximizes D sub A of M minus D sub A. Basically what this means is that you should always be trying to choose a move that, if you're winning, increases the lead on the other team, or if you're losing, closes the gap by the most amount. Much like in chess, the game is over when one team can only make moves that add to the progress of the other team. Now, if a team is winning a meet, and any move that they try to make will either add points to the opponent's score or keep their score the same, that's fine. Their best move in this case would be to do nothing, as it would keep their score the same. However, if a team is losing and can no longer make any moves that would benefit themselves, then the game is over because any move would lead to the victory of the opponent. In the case that the teams are tied and both teams can no longer make any moves, then no team can increase their score in relationship to the other team, so the meet must be declared a tie. After modeling swimmers, teams, and the game itself, I have taken all of this into account and written a program in Python that models these teams. The program creates objects that represent swimmers and teams, and it allows me to run a brute force algorithm that will run through all the possible moves and select the best ones for each team. I use this algorithm to help me discover the patterns of play to assist in the research of what moves are optimal and which is the best way to play this game. From writing and experimenting with this program, I learned a few key things. The first thing is that placing first is everything. Here are two examples of why this is true. First of all, if Team A has one swimmer in an event that was going to win the event, and Team B has three swimmers that will place second, third, and fourth in that event, then the total event score for that event is going to be 9-9. Meaning that their one swimmer accounted for the other three swimmers. And those three swimmers could have been in another event, but they needed to be in that event to counteract the top swimmer. For another example, let Team B have one person in an event and have that person be the only one entered in that event so far. That means that that team will have 9 points added to the score. Now, if Team A places a faster swimmer in that event, a swimmer that can beat the other team, then the event score becomes 9-5. Now, that's a net change of 14 in favor of Team A. To avoid such a huge point swing, Team B should make sure that they have a swimmer in that event that is going to win that event, no matter who the other team puts in that event. Another thing that I noticed is who goes first matters in determining the final point totals of the meet. While it doesn't affect the outcome itself, the point totals might be higher for one team depending on who goes first. The second player is always reacting to the first player's move, so typically when a team is going second, they'll score more points, but this is usually only marginal by a few points or so. If the teams are meant to tie, then the order doesn't seem to matter. If a team ties when Team A goes first, then the team will also tie when Team B goes first. I also noticed that who's winning and by how much matters usually. If a team is winning by a lot, then they will be less likely to find moves that will increase their score, which often makes the optimal move to be to do nothing. And if a losing team is losing by a lot, then the algorithm seems to terminate quickly because the team is a poor team and doesn't swim very fast. Something interesting I found when working with the algorithm is that there's a possibility for an infinite loop when trying to assign these people to events. We can let Jack be on Team A and Jill be on Team B. If Jack and Jill both have the same 4 main events, but Jack is faster in all of them, then the optimal placing will try to put Jack in every event that Jill is in to try to get more points. But we can see by this decision matrix that how the algorithm works is that it kind of goes in a circle. Let's say that Jack and Jill are both entered in the 50 free currently, and it's Jill's turn to make a move. It's in Jill's best interest to move to the 100 free because Jack's not in it, so she can win the event. So both Jack and Jill would score 9 points. Now, Jack can move to the 100 free and beat Jill, and then Jack would still get his 9 points, but Jill would lose 4 points. So, in relation, Jack would be up 4 points. Now that they're both in the 100 free, Jill should move to the 50 because Jill can win that event. And then Jack moves back to the 50 because Jack can beat Jill. And so the cycle continues. While it may not look like it at first, this is actually the matching penny game. If both Jack and Jill are in the same event, then Jack wins. But if Jack and Jill are in the opposite events, then Jill wins. As we've learned in class, the best solution here is to use the 50-50 mixed strategy, where half the time Jack chooses the 50 free and half the time Jack chooses the 100 free, and then the same goes for Jill. But in a meet, you only have one option, so this doesn't really work. The resolution here is to introduce a rule that stops teams from making the same moves twice. This will stop Jill from being re-entered into the 50 free after she has already been entered into it. At the time of this presentation, I'm currently using data from real swim teams to try to model and predict the outcome of those meets should they ever face each other. What I'm also looking to see is if two teams have already faced each other in real life, if my algorithm correctly predicted the outcome of the meet, or my algorithm could better assign swimmers to events for a team to score more points against the opponent. There's a broad range of future research that can be done in this area. First of all, are there other more complicated infinite loops that the algorithm can't handle? Also, is modeling teams like a game of chess truly optimal? Are there other ways for this to be done that can do it better? Also, I'd like to add in relays and diving eventually to this research. And this algorithm can be applied to more than just swimming. It can apply to a lot of different individual sports that have different point distributions, like track. Thank you very much.